An isoquant shows the different combinations of inputs needed to produce a certain amount of a good or service. For simplicity's sake, we'll analyze isoquants using only two inputs, capital and labor. The x-axis, or horizontal axis, shows the amount of capital needed for production, while the y-axis, or vertical axis, shows the amount of labor needed. Graphically, the shape of an isoquant will depend on the type of good or service we are looking at. In this case, the curve is the typical representation for a common isoquant line. All points along the curve give the same level of output. What changes is the combination of the production factors. The shape of the curve shows what amount of capital the producer can stop applying when increasing the amount of labor, while maintaining the quantity of output produced constant. For example, at this specific point we need 10 units of capital and 2 units of labor in order to produce a given amount of output. However, if we move along the curve, we get different input combinations, but always the same amount of produced output. This relation gives us the marginal rate of technical substitution between these inputs, which is the slope of the curve in each of its points. An increase in production will only come when we displace the isoquant curves outwards. The shape of the isoquant curves does not limit to this single example. There are an infinite number of possibilities. Let's review two particular shapes. Our second example is an isoquant map with 3 parallel lines. This is the case for inputs which are perfect substitutes, since the lines are parallel and their marginal rate of technical substitution is equal to 1, and it is why the slope has an angle of 45 degrees with each axis. Our third example shows an isoquant map with 3 isoquants that represent perfect complementary inputs. This means there will not be an increase on the amount produced unless both inputs increase in the required proportion. The best example of complementary inputs are shovels and diggers, since the amount of holes will not increase when there are extra shovels without diggers. Notice that the elbows are collinear, and the line crossing them defines the proportion in which each input needs to increase in order to have an increase in the production. In this case, the horizontal fragment of each isoquant has a marginal rate of technical substitution equal to 0, and the vertical fractions a marginal rate of technical substitution equal to infinite. Having defined and decided the optimal levels of capital and labor we need to produce the different quantities, the line that passes through these optimal levels is an isocline. In other words, it is the line that joins points where the marginal rate of technical substitution of each isoquant is constant. In the real world, the production functions do not usually follow symmetrical paths, and as a result, their isoquant's curve might look more similar to these. As we can see, the isocline line path will be altered. To sum up, the analysis of isoquants is very important when analyzing production. We should also keep in mind the relation between isoquants and the marginal rate of technical substitution and isoclines.